Yeah. Can you guys see my slides?
Yep.
Right. Okay. Thank you for introducing me. I'm studying in Imperial College London, and this is formalizing perfectoid fields. This is part of my master's thesis, supervised by Professor Kevin Buzzard. So let's begin. So, firstly, we have two worlds, sort of, because firstly we have number fields on one hand, which number theorists like to study. They are finite extensions of Q. For example, we have Q itself, or we can have Q adjoint I, or we can have Q adjoint square root of 2, or basically you can take any sort of irreducible polynomial and just adjoin a root of that polynomial, and you end up with a number field. These fields have characteristics 0, and number theorists like to study them. And on the other hand, the other world, sort of, we have a function field, which is a finite extension of fqt, where q is a power of a prime. So as an example, we have f37t. We also have f37 squared t. We also have f37 square root of t. Now these two fields, f37t and f37 square root of t, they are isomorphic as fields, but one typically considers this third one as a degree 2 extension of the second one. And these fields have characteristic p, and they arise from projective curves over finite fields. That's why they are called function fields, because they are the function fields of a curve, which like the stalk over the generic point in the algebraic geometric language. And so we have these two things. One have characteristic 0, and one has characteristic p. So on the surface, they seem kind of unrelated, but they actually share a lot of things in common. For example, we can complete both fields, both types of fields, I should say. So for example, the number field Q, we can choose a prime number P, and we can form the field of p-adic numbers using the p-adic norm. So we take the completion of Q under the p-adic norm, and we will end up with the p-adic numbers QP. So here the normalization typically doesn't matter, but for this talk, I have chosen to have the norm of P be P inverse. And similarly, given the function field fpt, we can use the t-adic norm sort of to form this Laurent series, where we just complete this field under this norm. And here I've chosen to set the norm of t to be p inverse as well, where the p comes from here. And so this is one thing that the two worlds have in common. And another thing is that we can find the rings of integers of the completions, actually. So this QP and FP Laurent series, we call them local fields because they are completions of global fields. So these two things, one has characteristic 0, this QP has characteristic 0, and FP Laurent series has characteristic P. And another thing in common is that we can form their rings of integers. The ring of integers of QP is ZP, and the ring of integers, I should recall, is that it's the set of elements, ring of elements with norm bounded by 1. And it has a unique maximal ideal generated by P, which makes it a local ring. I believe that's why QP is called that's sort of related to the word local in local field, but you can correct me if I'm wrong. And the residue field, which is the quotient by the maximal ideal, is Fp, the field with p elements. Similarly, we can take the long series over Fp. This has characteristic p, and the ring of integers will be the power series. And it also has a unique maximal ideal generated by T, and the residue field is once again Fp. So this is sort of the first hint that these two worlds, that one has characteristic 0 and one has characteristic p, these two worlds that are sort of related in some sense. So actually, these two number fields and function fields, they share a lot more things in common than these two slides, completions and ring of integers. So as you can see from this following NLab page on function field analogy, we have 5 pages of things that they share in common. So this is a sort of a big analogy of function fields and number fields. And but the question remains is how can we precisely connect QP and FP long series, these two sort of prototypical local fields, because okay, they both have a prime P, like they're both related to this prime P, and their residue field are both FP. Like the residue field we recall is the ring of integers quotient by the unique maximal ideal. So the residue fields are both FP, and is this a way that we can connect these two fields? So before we answer that, let's formulate the question more precisely. And by precisely, I don't mean formulate in lean, because this is still an informal question. The next step we ask is, how do extensions of these two local fields relate to each other? Or in other words, what can I say about the category of finite extensions of QP and FPT, or even finite Galois extensions, or some category related to that? Then so our first attempt is to exploit the fact that they have the same residue field, because residue field is functorial, right? So what I mean is that we can try to work with an extension of QP, right? And then we can also take a ring of integers, which will be an extension of ZP. And then you can quotient by P to get a ring extension of FP, right? This will typically not be a field. It will just be a ring. And but this is how we can sort of move from QP to the extensions of QP to extensions of FP, right? Given that if it's finite, because then there's some theorem that the norm can be uniquely extended to the extension. So the ring of integers is still defined, right? And given the extension of FPT, we can do the same thing to obtain an extension of FP, because this is also FP. Right? So we would like this to work, but unfortunately, it doesn't work, because we have two extensions of Q3 that produce the same extension of F3, right? Because if you adjoin square root of 3 and square root of -3, we can sort of trace what happens via this diagram. Right? So the first one is that you adjoin the square root of 3, and you take the ring of integers, and this will be Z3 adjoin square root of 3. And you can prove this because the minimal polynomial x squared minus 3 is an Eisenstein polynomial. So, and by that fact, you also have this sort of isomorphism. Yeah, and if you descend to F3, right? If you descend this extension to F3, then you get F3x mod x squared, right? Because 3 is the same as 0 in F3. So you kind of don't keep the 3 here, because so right. And if you start from Q3 with -3, then you can follow the same steps. The x squared plus 3, this is still an Eisenstein polynomial, and 3 is still 0, so you will still end up with the same extension, right? Or you can even generalize this, because this the only thing that makes this sort of counterexample work is that this minimal polynomial is Eisenstein, right? Because if you give any Eisenstein polynomial and you reduce it, like you descend to FP, then you're defining an Eisenstein polynomial will just become x to the n, right? So any two sort of totally ramified extensions of degree n will become the same if you descend it to FP, right? So this is sort of the hint that the reason this fails is because of ramification, right? Because of these extensions which reduce to x to the n, right? And so what is our solution to this? Well, in order to eliminate the ramifications, we first make this field make a very deeply, they say, deeply ramified extension in the mathematical jargon. In other terms, we'll adjoin all the p to the nth roots, right? So to QP, we will adjoin all the p to the nth roots of p, and we will denote this field this way: QP adjoin p to the 1 over p to the infinity. Because if this is n, because if infinity is replaced with n, then this is just the p to the nth root of p. So we just adjoin all of those roots. They are what make the extensions ramified, right? So you just adjoin all of those roots of p, right? And you end up with the ring of integers end up to be this, right? And you can still mod p, right? We are just working mod p. This is not a field, right? This is just a ring. And you can do the same thing here, right? Because you can adjoin all the p to the nth roots of t, right? And you can also take the ring of integers. You just turn all the round brackets to square brackets. And you also mod t here. We call that we do a mod t here, one mod p here, because they generate the original maximum ideal. Right? So there's mod p and mod p, and we end up with the isomorphic residue, not fields, residue rings. Maybe it's not really quotient by the maximum ideal, but you get sort of this same thing here. So they're isomorphic, and the isomorphism here sends p, like basically sends any root of p to the same root of t, basically, and this somehow works. This is apparently a big theorem. I think this is first proved by Fontaine and Vandenberger, and you can correct me if I'm wrong. And the content is that I will type out the names. It's Fontaine and Vandenberger. I hope I'm spelling them correctly. And so the theorem is that these, now if you do the same trick, right? If you do the same trick of taking one extension of this and descending it to an extension of this, right, then you somehow end up with the same thing, and you don't collapse different extensions. And so and you can do the same thing from here, right? The theorem is that this works under some sort of conditions, right? And or in the language of category theory, we say that the categories of finite, maybe Galois extensions are equivalent, the equivalent categories. Right? This is what corresponds means. Is yeah, and so this is somehow the solution. And so now, what's the perfectoid field? Well, what makes this work is that somehow if you mod p, then the pth power map is surjective, as in you can keep taking pth roots. This is what makes it works. So QP, it comes with the p-adic norm, right? Where the norm of p is the p inverse. we can join P to the nth root of P, and we end up with this field that we have seen before. And we can extend the norm to this field by this formula. And we can take the ring of integers. This will be the ring of integers. And then this, if you take the ring of integers and then you mod P. Right? If you remember this procedure, you take the ring of integers, you mod P. So you do the same thing here. You take the integers, you mod P. Then it is a ring of characteristic P. It is not a field. It's a ring. It's not even a neural domain. It's just a ring. It has characteristic P. And the Frobenius homomorphism, which is the P's power map, is surjective. Or in other words, we can keep taking P roots. And if we complete that, right? If we make this complete under the norm, under this norm here, right? We complete the field under this norm, i.e. if we take the completion, then we end up with what we call a perfectoid field, right? Which is precisely defined using this property, right? So, people have done this sort of equivalence of category stuff, this relating extensions stuff, right? People have done this over more generality, i.e. over perfectoid fields. This is just an example of a perfectoid field. This is the motivated example. If you look at the answer of, if you look at Peter Schultz's answers to math overflow, the question, what is a perfectoid space, right? The first example he says is this one, right? So this is sort of a motivating example. And so we call it a situation where we complete these fields, so to make our theory nicer. And right, so we call it, we take the ring of integers and then we mod P. So taking the completion, we don't need the completion here because the completion doesn't affect the quotient. They have the same quotient. And we do the same thing for the long series. And then we can, somehow we will have this situation where the extensions correspond to each other, right? And so note that this completion is non-trivial. This is not complete. In other words, the original field is a ring, or rather, this ring itself is not complete under the norm because the completion contains this sort of this type of objects, the power series, sort of, not really a power series, right? So why is it not in the original thing? Because the denominators keep getting bigger, right? But it is in the completion because the exponents here, they go to infinity. So this t to the exponents converges to 0. So the sum should exist if the field is complete. Right? So this completion is not trivial. And right. So one question is, okay, we have an extension of this QP thing. We can descend to an extension of this FP thing, right? And if we have an extension of this long series thing, we can descend to an extension here, right? But the question is whether we can go backwards. Like, can we go directly from here to here without just going this way and this way, right? From left to right. We want to go from QP directly to this FPT thing, right? And the answer is that this arrow somehow is very special because we can construct this middle field using this, right? In this diagram, we start with this and we mod T, but we can actually start with the mod T version and we can build up this ring back, right? And by this formula, we start from the mod T thing and we take the inverse limit over the P's power map. And somehow we get the middle ring, the thing whose field of fractions will be the long series thing, right? And this is called tilting. This whole thing from here to here is called tilting because of this relation here. And, this relation is like how we can build up ZP from the quotients. Yes, Frobenius is a homomorphism, so this X is not just T, but yeah. And ZP here, right? So you can build ZP from the quotients Z mod P and Z. And you can also build the power series by taking the inverse limit of quotients. And these two constructions are sort of actually the same because, okay, here you change the power, right? You change the power. So the corresponding thing would be to change the power here to say T and then T to the P, right? If you want to mod successively take quotients of higher powers, right? So the next step would be to mod T to the P, but it is actually the isomorphic, right? Because you already have P's roots. It doesn't matter if you mod T or if you mod T to the P, then you have the same thing. But the identification is this P's power map. So this is why we take the inverse limit of this instead, right? And somehow so in some sense, we can invert all of these arrows on the bottom row. So from here, from left to right, we do the same thing. We take ring of integers and we mod P. And this is isomorphic to this thing that we want to construct. But to go back here, we take the inverse limit of the P's power map. And to go from here to here, we take the field of fractions. So we call this the tilde of this. The bottom one here is the tilde of the top one here, sorry. So this special step here, we take the inverse limit of x to the p. We call this perfection in Lean. This part is formalized in Lean, not this equality, but the operator. You take the inverse limit. This part is formalized in Lean. It's called the perfection in Lean, and this operation is called perfection, and also we tilde is actually also a kind of perfection. If you remember this field that we started with, this characteristic zero field made from QP, you can take the inverse limit of the P's power map and you will end up with your target, this Lagrange series thing. But be careful that this P's power map is not a ring homomorphism, right? Because this field has characteristic zero, right? So this is not a ring perfection. So in Lean, we call this a monoid perfection because this P's power map is a monoid homomorphism. It preserves multiplication, it doesn't preserve addition. And in Lean, I've chosen to use the word monoid perfection. It's monoid dot perfection in Lean. And so any tilde is a sort of perfection. So, so now we move on to the formalization part, right? What that do in Lean, right? And what is the main point I want to address, right? Okay, so this diagram, right? We basically want to formalize this diagram in Lean, but there are problems here. What do you mean by ring of integers? Okay, yeah. So let's take an example: QP and ZP, right? We know that ZP is the ring of integers of QP. What does this precisely mean in Lean? How do we formalize this? Because we can't just say equality, right? Because okay, the left-hand side ZP, it can be defined in 100 different ways, right? You can define ZP using an inverse limit. You can define ZP as the Witt factors. You can I don't know if other constructions exist, but you can define ZP in a lot of ways. Right? I believe Johan has done some work on Witt factors. And on the right-hand side here, this is a subtype of QP. Right? This is formed from QP in type theory, in Lean dependent type theory. We call this as a subtype. Right? So how can a sort of Witt vectors, for example, how can the type of Witt vectors be equal, right? Equal to this subtype, right? This doesn't make sense, right? So what do we do, right? The answer is to use characteristic predicates, right? And what do we mean? So let's look at how we do it in Lean. So this QP is R because and it has an evaluation to the real numbers. And the ZP would be O. Usually we denote the ring of integers as O. So this is the characteristic predicate. This predicate characterizes uniquely what it means for something to be a ring of integers of some other thing. So firstly, the map, right? We need a map from the ring of integers, from ZP to QP. We need a map from ZP to QP, even if, let's say, we defined ZP as the vectors, QP somehow differently, right? Then we have a map here, the inclusion map, right? So this is just some map, right? Which we require to be injective. And we want to say that the range is exactly the ring of integers. How do we formalize this in a mean? We don't just say the range is the ring of integers because we want to be more explicit. We want to quantify over elements. We don't want to just say, we want to do, basically, we want to first order conditions, right? Basically, in a very loose sense of first order. So we say that, okay, this algebra map is the map from the ZP to QP. We want to say that the norm of everything in the range is at most 1, right? And we want to say that anything that has norm at most 1 comes from this ring of integers. This is precisely how we characterize being ring of integers. And this is in MATLAB. This code is in MATLAB here. The line numbers are here. And this is not enough for the theory of characteristic predicates to work. We also want to prove that this canonical construction of just taking the subtype, this canonical construction somehow gives us a ring of integers, right? So we need to build this, right? We need to build the canonical construction, sort of. We need to build the subring, right? The subtype of things of norm at most 1, right? And then after that, we want to show that this construction integer here is it satisfies this characteristic predicate, right? So this is the whole thing for the theory of characteristic predicates to work. And another thing in MATLAB that uses characteristic predicates is the theory of localizations, where we don't construct one sort of localization, right? We characterize maps that behaves like localization, and I think this part of MATLAB is formalized by Amelia Livingston, I believe, and so this is the theory of characteristic predicate. And another place where we will use this in a diagram, okay, ring of integers, okay, this is mod P. Maybe this also can be done using characteristic predicate, but I haven't done this. Maybe it's not really necessary because you're just mod P, but it can be used. The theory can be used here. Here, the perfection, I also use characteristic predicate for this. And also, the field of fractions here, this is already done as a part of localization. But there is in MATLAB, there is a characteristic predicate for field of fractions done by Amelia Livingston, I believe. And this perfection here, I formalized it in MATLAB. The characteristic predicate, I formalized it here. And this file, this is in MATLAB, but these two codes are in MATLAB. This perfection map here, I defined it here. This is a more complicated but still explicit definition. But this is a characteristic predicate. This uniquely characterizes some map being the perfection. And also, other than that, as I have mentioned before, I have constructed the perfection, right, as this sort of subtype of functions that functions. When I say functions here, I'm interpreting these as sequences, right? Sequence that each term is the pth root of the next of the previous. So so this is the canonical construction of perfection. This is basically an explicit implementation of the inverse limit. Right? The pth power limit is basically this one, right? And so this is how I do the characteristic predicate of perfection. So this is the end of my talk. Thank you very much for listening, and So I think this is question time now.
Are there any questions?
I have one question. If I
Yes.
so can I have you tried taking width vectors of your perfection? So can
Are
you?
you talking about here?
Yeah.
Yeah.
I mean, once you have your the perfection of FP double bracket T 1 over P infinity mod
This?
T. Yeah. Can you? So after all work done by Johan on width vectors, can you take width vectors?
Rob. It's Johan and Rob.
Johan and Rob.
I do the first time round, but
thank you, Kevin, thank you very much. I'm sorry, Johan and Rob's work on width vectors. Can you take width vectors of these things, because they were basically taking width vectors of finite rings?
I thought Johann's work made it possible to take width vectors of any characteristic P ring. I might be wrong. But Johann can confirm.
Or Rob.
You can take width vectors of any ring. Whether you can prove something about the result is of course a different question.
But you're not going to get. This is a very strange situation, because you're not going to get ZP P to the 1 over P to the infinity, because you're going to have a uniform, right? The width vectors always have this kind of canonical uniformizer, right? There's I find it hard to believe that you'll get. I might be wrong.
Isn't this where your B Diram thing comes from, or what?
Yes, exactly. I mean,
yes,
this was
that's somehow what you're on the way to defining.
B inf, or
yes, a inf, isn't it? Or
a inf, yes.
A inf. I think I've always been brought up to say it, because it's French people made it all. But yeah, this is funny. But before you take all the P power roots, you can build your way up along the top using width vectors, but somehow the bottom is mysterious. And when you throw in all these P power roots, the observation is now the bottom has become much less mysterious, because you can just make it using perfections. And now I don't know whether the top line is mysterious or not. In fact, I have a related question, Kenny. You pointed out that just using monoid perfections, you can go straight from the thing on the very left, from one end of the map to the other, right?
Right, but the thing is, I don't know if you can define addition, right? Because this is. Yeah.
But remember, what Amelia showed us. Well, I guess what Bourbaki showed us with monoid localization was that you can do monoid localization on monoids, and if the original monoid has a ring structure, then under many circumstances the localization has a ring structure. And is that what's happening here?
But the addition is not pointwise, right? Because you need to somehow take a limit.
I know, but what I'm saying is
there is a
if you have
general.
If you have a ring and you take the monoid just a general ring might not have characteristic P, and then you take the monoid perfection of it.
Yeah, this definitely does not have characteristic P.
Right, but if you take the monoid perfection of a characteristic 0 ring, can you always give it a ring structure?
Right, but you need P power roots, right? The construction in Catalan, I think, has this, right? You need P power roots. Given A and B, right? You take P to the nth power root of A. You take P to the power of the nth root of B. You add them together, right? And then you take P to the nth power of this whole thing, right? And then this is the limit of this as n goes to infinity. I think this is the result of A plus B, I think.
Right. I've just noticed the time. We should probably take this offline. But I mean, firstly, thank you very much for your talk.
Thank you.
And secondly, I guess, in particular,